So Brad is going to present on collimating and
aligning your finder scope, which are intimately related.
Yes. Yeah. And then Jason is going to present on polar alignment. Joanne is going to talk about magnification and field of view. Eyepieces. And then I'm going to wrap up with some useful accessories. So, please everyone, welcome Brad.
I'm Brad. How's it going? I've already introduced myself, so I will skip the pleasantries. So I'm going to talk about your telescope. Now, I have wandered fields throughout the world and looked through many a scope, and many of them give images that are not all that good. I've seen bad images. And the most common problem that I see is an easy one to fix. It is that the telescopes are out of collimation. So what I want to do is tell you what that means and tell you how to fix it. So first of all, let's take a look at why we need to collimate. Now this is a simulated image of the field of view of a telescope. This is here, the center of the telescope field of view, and as you go further and further out, these stars actually stretch out. They acquire what is known as coma, which is, which I will describe here. So, let's take a look. So most of the time, when you're looking through your telescope, you're actually looking through a very small portion of the overall field of view of the telescope. You're looking only right here in the center. This is like the field stop of the inside of your eyepiece. So in this particular case, most of the stars within the field of view are looking pretty sharp. They don't have a lot of that stretchy thing that the stars are doing right out there on the side. They're not subjected to coma. Now, if you had a smaller field of view right here, your collimation would be, your stars would be even sharper if you were right here. If you had a larger field of view, you would be pulling in stars that had a little bit of coma to them. So let's take a look at what happens when you're out of collimation. When you're out of collimation, you're actually looking at a part of that field of view that the telescope creates that's not in the center. You're looking off to the side. And so your field of view is going to be filled with star images that all have coma. And that affects the view. So let's take a look at how that affects the view. Here's a picture of Saturn before collimation, after collimation. It will make your views look sharper if you get your field of view centered on the telescope's field of view. On the telescope's field of view. You get that? You get those, the place that the telescope is looking right where the stars are the sharpest. That is basically all collimation is. Now there's, so let's take a look and see what happens with a telescope. A telescope makes an image by taking a shaft of light and bringing it to a point. So when the point is centered, that point is going to be in the center of your field of view. If the telescope image, now notice the difference between these two, the red comes a little bit from off the side, then the image will actually be diverted up here to the top. So it went from here to up here. It'll be diverted a little bit away. So this particular, if it's slightly off axis, this particular part of the field of view will be subjected to a little bit of coma because it's not in the center of that sweet spot. It's a little bit off the center. And if you go the other way, the same thing will happen. If the image just goes the other way, the same thing will happen. So here's what happens when everything is on axis and you're looking right in the center. All the lines come together. Now this is not assuming any chromatic aberration. You're not having any chromatic aberration from a mirror there. If you're off axis, what ends up happening is that the parabola of the mirror is not able to bring all of the lines of starlight to a single point. Here, when it's on axis, it's able to bring everything to a single point, and here, when it's off axis, it's not able to bring everything to a single point. This is good, this is bad. So when things are off axis, you're not going to see things as well. Now, a second thing can happen is within a Newtonian telescope, you have a second mirror here. And sometimes that second mirror can actually not gather up all the light from the primary mirror. So in this case, what's happening is you're getting light that comes down from this particular, hitting the main mirror, and then when it gets reflected back up, only a little bit of the light that comes back up is hitting the secondary and getting deflected off to the side. That adds coma, that also adds distortion to the image. So if the light cone here is missing the secondary, you're not going to get a good image. You're not going to get a good image like that. South Park. So let's take a look. So here's all of the light cones all added together. I just thought it was a pretty picture. So let's take a look at what that actually does to a star image. So right here, this is actually what is called an airy disk. This is the finest point that a telescope is able to resolve. A telescope is able to take light, shrink it down into more or less an infinitesimal point, except that the wave nature of light prohibits it from getting infinitesimally small. It has this weird wavy pattern, and that's basically the way a star image looks like under ideal conditions when you have a telescope image. If you were to magnify a star with a perfect mirror under perfect seeing, this is what a star would look like when everything was all lined up perfectly. When the star is off-center and you're getting a little bit of coma, or you're looking in that non-sweet spot, the star image will be distorted here. This is what ends up happening with the star image. You get stretched out, and that's actually what causes the coma, is this stretching out. So if you do this a whole lot, if you get a whole lot of coma, you end up going from something like a point, and the star image gets bigger and bigger and bigger depending on how far off you go. So this here is a star image that is way off center. It's not in that central sweet spot. So how do you collimate? What do you need to do? Well, the first thing you need to do is figure out how to line up the secondary mirror. This is the little mirror I'm going to show you here. There's a little mirror inside this particular telescope. This telescope's great because you can actually see inside of it. This little secondary mirror in a Newtonian telescope points down at the primary. It has to be directly pointed at the primary. So the first thing you want to do is you need to figure out how to line up the secondary with the primary. So that secondary is seeing the whole primary. So here's an image on the left of a telescope. This is actually looking down the tube like this. And notice how we're not seeing the whole mirror. This is the edge of the mirror right here. And the other edge is hidden a little bit by the telescope tube. So there's a number of tools you can use. I was happily loaned one of these. This is called a cat's eye eyepiece. However, you can actually use a very simple tool, and I'll show you something that is perhaps a little easier. And you stick this little guy in here. And all this is a little hole inside of a cap that you put into your telescope tube, and you look down it, and all that this is doing is it's centering your field of view on the axis of your telescope, where you want your telescope eyepiece to sit. It puts it right in the center. You look, and the goal is to get your secondary not looking like this, but like this. Now notice you're seeing these three little lines here. Those are the clamps that hold on to the secondary mirror. This secondary mirror is centered. The way you collimate the secondary is most secondaries have these little screws here.
Those are the clamps that hold the primary.
These clamps here are the clamps that hold in the secondary mirror, right there. So those are the ones that hold on the secondary mirror. Now I'll show you how to do that in a little bit. But so the first thing you need to do in order to get collimation to work, if you don't do it in this order, you'll need to go back and actually fix it because you'll be off. So the first thing you need to do is line up the secondary, and the easiest way to do that is to get one of these little Cheshire eyepieces, or there's another thing that I can show you, and basically line up the secondary by looking through this little Cheshire eyepiece. Now the Cheshire eyepiece also has a little bit of extra reflectivity to make it visible and that kind of thing, but that's not the critical element. The critical element is visually getting it centered in that field of view. So here's what you're looking at. So when you're looking down the telescope tube, this is the inside of the tube right here. This is the edge of the secondary right around here. And then you're seeing the whole primary mirror here. You're seeing the whole primary mirror in the secondary mirror. There's a little bit of a gap around it. And as long as this view of the primary mirror in the secondary is all the way in view, you're good. You're good to go. So now, the other thing is, if you have a large Dobsonian, it'll be slightly different. You'll probably have this center dot at the center. You want to get that in the center of the field of view from your secondary. So when you're looking through this little secondary dot will need to be in the center. So we can keep going. Now, there's a little tool that you can use. Now, this is getting less and less common, but I bet a few of you might have one of these things around in your basement. This is a thing called a film canister. Does anybody remember that? Does anybody? Yes. Okay. A film canister. People used to use this weird plastic substance called film in order to take pictures. You used to have to take them to a store and do that. These things work really well as a little Cheshire eyepiece. So if you happen to have one of these things lying around, it works pretty well. So that's a good way to align your secondary. The other thing is you can actually buy one of these things. You could buy this one. This is mine that I own, and it's incredibly easy to do. I mean, these things cost about $25. So let's ignore that. Since I want to go here real quickly. Now, the critical part is once you've aligned the secondary, you need to align the primary. And I'm going to teach you a method that doesn't actually require you to own any equipment. You don't have to actually buy a laser collimator or anything like that in order to do this. There are specific pieces of equipment that allow you to do that. So what you need to do is you use the sky. You get your telescope out, you let it cool down, which is very important because if the telescope mirror is warm, you won't actually be able to see the image that you're attempting to use to collimate the telescope very well. And once your telescope is all cool, the air is all steady, you defocus a star image. You actually back out the telescope. You move the telescope out and away from you. And ideally, when you do that, you should see a picture of the primary mirror defocused here. And at the center, there'll be this little ring right here, and it's all distorted by diffraction effects and that kind of thing. But you'll get this image. This is kind of what you're going for. This is the star image in focus. This is the star image out of focus. Now, which star do you want to do this on? You want to do it on kind of a medium bright star, and one that's not going to move around a lot because you're going to be working with this a lot. A really good star to do this on is Polaris, the North Star, and the reason why is it doesn't move. You know, you're not going to be constantly readjusting. If you picked Vega or Altair or something like that, every 2 minutes you'd have to readjust your telescope. And the other thing is you need to use high power. You can get a lot better precision by cranking up the power to 200 or 300 power before you actually do this. So what are you doing? Well, what you want to do is you want to get a star image where this ring, this donut hole in the star image is centered. This is good, fairly good. It's not perfect, and this is bad. So you don't want this, and you do want this. So how do you do this? So you do what I call the collimation dance. The collimation dance is you look through the eyepiece, then you go down and you turn a knob. And then you go back to the eyepiece, and you see which way the star moved. Did it move in the correct direction? If it did, then you go back down and you move it again. Did it move in the correct direction? No? Okay, then you go back. You do the collimation dance. Now, if you're doing it alone, this is what you have to do. You have to do the collimation dance. My favorite thing to do, however, is go, Wilkie, could you help me collimate my scope, turn a knob down there? Oh, and be careful of the fan on the bottom of the scope. It'll grind up your fingers, please. Thank you. So that's what I will do, is I will enlist a friend. So let's see what you're looking for. You're looking for this dot here to move in the correct direction. You want it to be centered. Now, if you back out the focus, meaning you bring the eyepiece toward your face, when the dot is moving relative to this figure here, when this dot is moving relative to this figure, the entire thing is moving much more quickly in the direction of the image itself. So as the telescope is actually pointed in a new direction, as your friend moves that little knob on the back of the telescope, this entire image will move. The thing inside of it, this thing, will move at a slower speed relative to the overall image. You'll actually get that little donut hole will move a little bit relative. How much time have I got?
On your first presentation,
Yes.
not much time.
Not much time. How much time overall?
I was late starting it, so I'm
Okay.
not sure exactly.
Okay.
You have about 12 minutes or
Okay, thank you. So I'm pretty good. I'll be on time. So basically, what you want to do is you want to watch which direction this whole thing moves. If this thing is moving in the proper direction, if the whole thing is moving in the proper direction, then this thing will be moving relative to the overall figure. See, it's going to go from something like this to something like this. This little dot moves a lot slower. So that's a good way of doing it. And remember, you have to have backed out the focus for this to work. If you crank it in, you'll get the same effect, but it'll go in the opposite direction, which is very confusing. So there are three little knobs on the back of your scope. So this is still the collimation dance. Now, at the very end, it's kind of hard to tell where that ring is relative to the star image, the defocused star image. And there's a little bit you can do to kind of fine tune it. So it's hard to tell. Is that centered? I don't know. I don't know. But there is something going on here. You'll notice that the top of this guy right here is a little bit brighter than the bottom. This is an indication that a little bit of that star image is still squished up there near the top, and there's more bright light on that side. So you still need to move this guy downward a little bit to bring it a little bit away. This is called collimating with a star collimation. And it's probably the most accurate and easiest way to collimate, because you don't need any equipment except for maybe a friend to kind of help you out and that kind of thing. So there we're looking at the bright ring. That's a key for that. So how do you actually do the collimation? Well, most telescopes have little knobs on the back, and you're going to have several different knobs. This one has 99% of them have 3 knobs. If they have 4 knobs, go complain, because there's no reason to have 4 knobs, because that's superfluous. You only need 3 knobs, or even just 2 and 1 that's fixed. So when you start to collimate, the first thing you need to do is turn a knob and figure out whether or not the star is going in the right direction. You've already learned where it needs to go in the right direction. So I turn this knob, I turn it in the right direction. Is the star moving in the correct direction? It's not. I'll back it back up again, and then I'll try this knob. It's very simple. You just need to experiment until you find it out. There's no way to remember which knob turns the star which way in the sky. I never even try. I just say, hey, pick a knob, and then is it right? Yes, it's right. If it's not, then I say, okay, try another knob. And then by doing that, you can experiment and figure out which knob moves that donut hole in the right direction relative to the star. So there are other slightly more yes?
Since there's only 3 knobs, does it sometimes require a combination of 2 dots together.
Yes, exactly, yeah. So, yeah, it's always going to require, I mean, ideally, you will be using two, sometimes you use all three. Sometimes you'll actually end up with one knob being cranked in all the way, and you won't be able to go any further, so you'll have to back the other two out in order to get more, in order to get more movement and that kind of thing. You have to figure out what the mechanics are. Every telescope is going to be different in that regard. I mean, I built my own little telescope, and it's got its own little idiosyncrasies. Now, there are different types of telescope rear ends here that you need to deal with, and one of the more common ones in commercial telescopes, like your Meade or Orion cheap Dobsonian style telescopes, or Newtonian style telescopes, you'll get these little guys here. And these are called push-pull telescopes. You'll have two different screws on the back, and usually you'll have one screw which kind of locks the mirror in place, and the other screw which pushes against the mirror. So one screw will push, and the other one will pull. The other, So what you'll do is you'll need to, in order to collimate, you'll need to loosen the ones that hold the mirror in place, then do the collimation, and then very gently screw these things back up so they nestle up against the back of the mirror. So you will unscrew these guys in order to loosen up the telescope mirror and allow it to fly freely, and then you'll collimate and then screw those gently back in. Double check your work because it's possible for these things to kind of screw things up. But the advantage of this particular type of system is that they can grab the telescope mirror from two different directions and hold it in place. And it's not likely that your mirror is going to get knocked out of collimation really easily. So it's likely that you'll be able to handle the situation and not have to deal with it again for a very long time. The other thing is, if you have a Schmidt-Cassegrain telescope, you only have to collimate one thing. You have to collimate the secondary mirror. And the way you do that is you look at a star image. You can't do this with a laser. You look at a star image, and then you just use whatever tool is necessary to turn the three little screws in the Schmidt-Cassegrain mirror. You basically need to star collimate a Schmidt-Cassegrain telescope. It's all in the secondary. You don't need to worry about moving the primary around. So generally, the secondary mirror of a telescope is also going to have its own set of tools, which are inevitably easy to lose. Usually there's an Allen wrench or some sort of thing. Every single system is different. There's no universal way of doing it. My obsession has wing nuts that you screw in. It's just very simple. This particular one has an Allen wrench that you will probably lose and need to go buy another one. But it's actually quite simple. Now I'm going to demonstrate a slightly easier way of doing this, and it has an advantage of actually being able to be done during the daytime. Yes, 5 minutes? 5 minutes, I'm almost done. And it's by using a laser collimator, and there are dozens of different types of these. This is a real expensive one that has a very fancy image that comes out of it, and that kind of thing. But you can get the cheapest laser collimator and do this. All you need is the laser collimator and either a Barlow or this little device that's called a BLEG, B-L-E-G. And it's got a little tiny Barlow lens in there that smears out the light. Basically, it smears out the light, and all you do is you put this on here, like that. And what happens with this BLEG is when you turn on see how that blurs the image a little bit? Remember how it was a nice, fine, sharp view? What you do is, if your telescope, like this one, has either a secondary ring or a dot, and this one does, I don't know if you guys can see that, but if you look down there, there's a little dot. You put in your laser pointer. Actually, I need a finder here. Let's see, where is it? Okay, I lost my Howie Glider paralyzer, so I'm going to just use the one that came with the scope. Put this in there, turn it on, and then what ends up happening is you end up getting an image of the mirror reflected back up at this little white part here, this little blade. These things are about 40 bucks. Now you'll notice right here, and I can't quite, you have to kind of look at it, and I can show you it later on outside. There's a little shadow right there, just next to that, just next to the center of the hole. That shadow is the shadow of the dot. And what you want to do in order to collimate this is basically turn the telescope until that dot is centered. Now I'm going to move this, and I won't be able to see it because I'm showing you guys, but is it going the right way? Isaac? Right way? Wrong way?
Wrong way.
Wrong way? This way?
That way.
That way? Okay. So, and eventually, what happens is, if that little shadow, either, if it's a ring, surrounds the hole that the laser is coming out of, or if it's a dot, it goes back in the way it came. Basically, that means everything is lined up. The advantage of this is called Barlow collimation. You can actually, if you set these things on if you set these things on this little Barlow here, you don't have to worry about the alignment of your laser pointer, because the light that is reflecting out is getting smeared out, and all that you're doing is looking at the reflection of that dot, and the reflection of that dot will be a precise indication of where the center of that mirror is. You don't have to worry about that. So if you use this Barlow technique, you can get very, very accurate collimation without having to use the star collimation. But you can always use star collimation. Now, the other thing that you have to do, of course, in this, and I'm just going to mention this in passing, is once you've collimated your telescope, if you actually ended up moving it, your finder scope on your telescope is going to be, your finder scope is actually going to be not pointing in the right direction. So what you need to do is you need to get your finder scope pointed in the correct direction. So the way to do that is to find a nice bright star that you can actually center in the field of view. Put an eyepiece in your telescope. Find a nice bright star. It could be any old star. The brighter the better, because then it's easier to find. And then, once it's centered in the field of view of your telescope, not the finder scope, then go to the finder scope and center up the star afterward. And that will actually bring the finder scope into alignment with your telescope. Often using a planet or the moon helps. If you get the moon perfectly centered in your field of view, then go over to your finder scope, get the moon perfectly centered in your finder scope, and you're good to go. But the two always go hand in hand. Whenever you collimate your telescope, you're changing the way the telescope points into space. So that's pretty much my part of the presentation. If you guys want me to help you collimate a telescope, I'd be happy to give it a try on this one outside, and we can go ahead, we can put this to practice. Yes?
One thing I might add, and it's pretty important, you can go back to that one picture, back one where, one more, yeah, right there.
That one, yeah.
Whenever you're using an Allen wrench or a screwdriver to adjust your secondary, make sure your optical tube assembly is very close to horizontal.
Yes.
Because if you drop your Allen wrench or
Yeah.
your screwdriver, it will land on your...
It will land on your primary and do damage. The Hidden Hollow campground, the folks that were that used the Warren Rupp Observatory, they had a beautiful 31-inch mirror, probably the finest 31-inch mirror ever made by Norm Overly. They were working with their secondary, and they actually ended up loosening the secondary so much that it fell on the primary and shattered it. Imagine the pregnant pause when they waited for it to hit that mirror. And they ended up having to get a new telescope mirror, and many thousands of dollars. So yeah, when you're doing this, point your telescope down a little bit so if you drop something, it falls into the tube and not on the valuable telescope.
Or use a string.
Yeah, or use a string. Yeah, that's true. So yes. Okay.
All right.
Okay. Thank you so much.
We'll probably have to take questions after.
All right, so I'm going to be talking about polar alignment. A lot of, like this telescope, that telescope, you don't have to worry about polar alignment. If you get what's called an equatorial mount, like a German equatorial or a wedge for stochastic grains, you're going to need to do something called polar alignment. Let's talk about what is polar alignment. So the whole idea with polar alignment is if you're not using a clock drive, so everybody knows that the Earth moves, right? You know, we're standing on a planet that's turning in circles, while it causes things to rise and set. So what you want to do, believe it or not, yeah, really that's the case. So what you want to do, you want the telescope, because if you look at this planet or something in the telescope, it starts moving across the field of view. The reason why is because the Earth moves. Well, telescopes have clock drives that allow us to counter that movement, and when we polar align, it makes that clock drive work. If you don't have a clock drive, but it's still an equatorial mount, it allows you to make adjustments with one knob only instead of two knobs at the same time, which can get kind of annoying. So like with an all-azimuth like this, you are moving it in two directions in both altitude and azimuth in order to keep things aligned. With an equatorial scope, you don't have to do that. Now, for astrophotography, polar alignment is absolutely essential so that you can keep the object in the same field of view as you're taking a picture. If you don't, you'll start to get what are called star trails. You can do that with all azimuth mounts that will track, but you get what's called field rotation after you're taking longer term photos, because as it's adjusting, the entire sky is kind of rotating as it's going across the sky. So polar alignment is very important for astrophotography, and it makes observing more relaxing. So what is it? So what we're doing, there's an axis, actually it's called the right ascension axis. It's also called the polar axis. And what you want to do is you want to align that polar axis to the center of rotation of the sky. The center of rotation of the sky, if you stood straight on the North Pole, would be straight up, because the Earth is rotating, so the sky tends to, the sky turns, and that's the center of rotation for the sky. So you want this polar axis to point straight to what's called the celestial pole. A lot of people think the North Star is on the celestial pole. It's not, it's about 2 degrees off from it. So the North Star actually makes a 4-degree circle as it goes around the sky. So it all has, like, if we took this telescope and we put it on the North Pole, this would be polar aligned. Of course, I don't know if I'd want to observe on the North Pole, but this would be completely polar aligned. So what essentially we're doing, we are taking an all-PAS mount and tilting it to basically 90 degrees minus your latitude, 50 degrees, so that it is the center of, or the polar axis, which for an all-azimuth telescope is straight down in the center. So we're basically tilting it up so that center is up towards the polar axis, or the pole. I won't get into it. There are things called equatorial platforms where you don't have to do that, but I'm not going to get into that. So perfect alignment means that you don't have to do any adjustments in declination. What that means, I wish I had a telescope here that was like that, but declination is essentially right ascension is going this way in the sky, declination is going north and south. So right ascension is east-west, north-south is declination. So once you have your telescope lined up perfectly, it's tracking the sky going this way, actually, yeah. So it's going this way, and then all you have to do if you want to change the declination, you just change it going up and down to go to a different part of the sky. So we'll talk about how we polar align. First thing we want to do is, I use my phone because it's got a compass on it, and you can do this during the daytime. You take your telescope tripod, and usually you'll have one of the tripod legs will have like an N on it, or you'll know that that's the one that's supposed to point towards the north. There's usually a little, like a mount or something on there that indicates, I had a question. So that will allow you to do the adjustments. Oh, there we go, thank you. Alright, so what you want to do is you want to point, so in this particular case, now, this is north on this particular telescope. This direction is, or this is the polar axis pointing up towards where the celestial pole is. So you want to level the tripod first. You could use your phone. I use my phone to do the level. You can use the compass on there to get it into the rough area where the North Star, or I'm sorry, where the celestial pole is going to be. But you want the telescope mount to be level, because if it's not level, you're going to introduce errors the longer you track. So when the stars come out, you look for the North Star. And the way you do that, you look for, you look for the Big Dipper here. You have these two stars that point toward, they're called the pointer stars, points toward the North Star. So once you are lined up to roughly north, you can center the North Star in your telescope, and that will be fine if you want to do just visual observing. If you want to do like photography and things like that, you'll need to use something called a polar alignment scope. And most telescope mounts will come with a polar alignment scope. And it's like this little mini telescope that goes at the bottom of the polar axis, and it has an opening here. And inside of there, you'll see something like that, where you rotate the pole. There's like a reticle that you can rotate so that the orientation of the Big Dipper and Cassiopeia, we don't have to worry about octants because that's the southern hemisphere. But, so like this particular case, this is kind of like late summer, if the Milky Way is towards that orientation, Milky Way, the Big Dipper. Wintertime it's on the bottom, spring, or actually no, fall it's on the bottom, spring is on the side, winter is on the side, spring is on the top, summer is on the side. So that's, you just look up and find out where the Big Dipper is. You orient this until it kind of is in that direction. Then you use your azimuth knob, which in this particular case is this guy. And you just turn it like this. This is the azimuth knob. Or the altitude knob. This is what adjusts it going up and down. And in this particular telescope, there's right here. And you center that, or you move that, and those are going to take two things you move. You don't want to move the declination at all. Until Polaris is inside of that circle. So right now, Polaris would be about right there. Now, if the Big Dipper was down here, Polaris would be on this side. If it was up here, you can kind of get the idea. This orients where Polaris should be in relative position to the north celestial pole right there. So if you don't have a polar alignment scope, really all you need to do is point your telescope so you see Polaris in the field of view, and that should be adequate for most visual observing. If you're doing astrophotography, invest in a polar alignment scope, but not too expensive. If you want to really get accurate polar alignment, there's something called the drift method, which I will not get into today, because it's pretty involved, but it's not too hard. But you can look that up on Google, because that's how I find out everything. So this just kind of gives you an example of what it looks like. Essentially, you're fine-tuning your telescope. You point it to a star at a certain position of the sky. You let it run for 5 minutes, and as it drifts a certain direction, you can make small adjustments, and you repeat the process. And you keep doing that for probably about a half an hour. I found that I do not need to do those kinds of things. But if you had like a pier and you're setting up an observatory, this is definitely something that you want to use. There's also software-assisted polar alignment mechanisms that I thought that was out of scope for this. Anyway, so that's pretty much it that I had. Did I make it?
You made it. It's 15 seconds.
Do the moon and planets respect the rotational axis of the star?
Yeah, they do. For visual use, you shouldn't see too much of a difference between the moon's movement or the planet's movement. But for like serious planetary astronomy, they do move at a different rate than the rest of the sky. So if you're doing like long-term astrophotography, and you don't take long-term photos of the moon, you may take a long video so that you can stack all the different frames. You may want to adjust it so that your tracking is tracking the moon instead of the celestial sphere. But for 9 times out of 10, you wouldn't have to worry about that.
Thanks, Jason.
Yep.
There you go, one more question.
Oh, I just wanted to add, as far as polar alignment goes, if you're using a lot of the go-to mounts these days have polar alignment routines in them, so if you can't see Polaris, Celestium's got a good one called All-Star Polar Alignment, and that's relatively accessible to consumers at the price point. And there's also an app if you don't have a polariscope. When I first started astrophotography, I used that a lot. So you don't have to be super accurate, but it'll show you kind of where Polaris should be within the circle or the field of view. So lots of quick, easy ways to do it when you're starting out.
Thanks, Jason.
First, I want to speak a little bit about eyepieces, magnification, field of view. I'm not a very good speaker, so please bear with me. What is an eyepiece? Well, for those who don't know, it's a little round thing with an eyepiece holder here, and it allows you to see the light that comes out through the telescope. The telescope would be useless without an eyepiece unless you're doing astrophotography and put a camera in it. Basically, this is the way they work. Objective, which would be either a lens or a mirror, collects the light, it comes into focus, and then it goes on to the eyepiece. The eyepiece takes that light, magnifies the image, and brings it to focus in your retina. Without the eyepiece, you wouldn't be able to see what the telescope has gathered. Okay. To determine the magnification, you have to know, first of all, the telescope's focal length. That is the length from the light that bounces in the mirror up to the secondary or the lens on the refractor and out into the eyepiece and comes to focus. And then you put the eyepiece in there and that will magnify it. So you need to know the length of that focal length. Usually is, you have like a, say, a 10-inch f4. So the focal length would be 10 inches times 4, 40 inches. You have to change that into millimeters. That means multiplying by 25. And that's your focal length. The eyepiece focal length is usually printed on the eyepiece. It'll say 50 millimeters, 25 millimeters, 80 millimeters, whatever it is, it's usually written on the eyepiece. By dividing the focal length by the eyepiece focal length, you get the magnification, which means an eyepiece that will give me a magnification of 30 power on this scope may give me 50 power on that scope because they have different focal lengths. So you cannot just look at an eyepiece and say, how much does it magnify? No. You have to know the instrument is the combination of the two that determines the magnification. Like I said, the larger number on the eyepiece, a 30 millimeter, say, is going to give you a lower magnification than an 8 millimeter. So it's backwards. So if you want something with low magnification, you go for a large number. If you want something with higher magnification, you have to go for an eyepiece with a lower number. And like I said, it will result in different magnification. And remember to convert all measurements into millimeters before you figure it out. There are tables out there, by the way. You'll probably find them in almost any astronomy-related website that will give you the ratio between one and instrument and the eyepieces. There's an eyepiece that Brad mentioned called the Barlow lens. The Barlow lens is not used alone. It's a special eyepiece that you put between the regular eyepiece and your mirror. And it actually will double or triple depending on the Barlow, the magnification of the original eyepiece. So you can have an eyepiece that gives you, let's say, 30 or 20 power, and, or 30 or 40 power, you use it with the Barlow, and you automatically are doubling your eyepieces, because then you're going to get 60 power instead. How many eyepieces do you need? I'd say a minimum of 3. A low power eyepiece is probably your best friend when it comes to finding objects in the sky. You use a low power eyepiece because it has a bigger field of view, you'll see more, and you'll be able to find, let's say you're looking for Jupiter. If you're using a low power eyepiece, you'll see more of the sky, you'll be able to find Jupiter, center it, and then go on to your medium eyepiece, which will offer you much better, closer views. The higher power eyepiece is usually safe for those special nights when everything is clear and it's steady. Not so much clear, because you will find out that sometimes at night that it's a little hazy, will offer you better seeing than the night that everything is twinkling, which indicates a lot of movement up there in the atmosphere. So depending on your interests is the kind of eyepieces and the kind of power you want to use. If you're someone like me that I like what they call like big faint fuzzies, galaxies, nebula, things like that, I tend to use lower to medium eyepieces. If you are in planetary observing, on the other hand, you may have slightly higher power to begin with and go to much higher power than I will ever use with my telescope setup. Field of view is how much of the sky you can see through a given eyepiece. A lower magnification eyepiece will have, you'll notice the sizes of the lenses. They'll have a big lens. You look up to the sky and let's say it's what they call the apparent, okay, here. The apparent field of view, you hold the eyepiece up to the sky and how much of that sky you can see through the eyepiece, not through the telescope, but just through the eyepiece, is your apparent field of view. So something with a large apparent field of view will be easier to see through because sometimes they get to the point where you're looking through a little tiny lens with a very restricted field of view. And that makes it a little harder to observe. Then the true field of view is you take the apparent field of view, which is already given by the manufacturer, you know, it's usually a field of view of 50 degrees, field of view 25 degrees, and you divide it by the magnification of your scope eyepiece combination. So if your magnification is 30 and your eyepiece is a 60-degree field of view, you have a true field of view of 2 degrees, for example. So a wider field of view means that you will see more through your eyepiece when you're observing than the same magnification with a smaller field of view. And that's where you have the wide field eyepieces, extra wide field eyepieces. That's when they hit you at $100 for an eyepiece. Eye relief is the distance that you have to hold your eye when observing from the eyepiece. And the smaller lenses, the higher power eyepieces, usually have a lower eye relief. So you have to look closer and closer. And if you wear glasses, that can be a problem. Now, that's where the Barlow comes in. Because you can use, let's say that you want to have 180 magnification, you can use an eyepiece that has lower magnification, 90 power, and it's a lot more comfortable to look through. Put your Barlow in that doubles your power, you still have the eye relief of the original eyepiece, and you don't have to just cram your eye in there trying to see what's in the eyepiece. So a Barlow lens does introduce another lens into the system, which means just a little bit more light bounces around in the total system, but it can make the viewing a whole lot more comfortable. Then there's add-ons that you can add to your eyepieces. Most eyepieces are threaded inside. You can put in filters. For example, you like to look at the moon, but you don't want to go out there tonight and get blinded by the moon. You use a neutral lucidity filter, you use a polarizing filter. They call it moon filters. They're relatively cheap, about 15, 20 bucks. You screw it into the eyepiece, you look at the eyepiece, and all of a sudden you can see the craters without being blinded. You can have light pollution filters, which will only let a narrow part of the light go through, but it will block out the lines from the beautiful light that your neighbor decided to put next door. And it will bring out more contrast and make it a lot easier to see some of the wonders of the sky. There's some that are only useful of 1 or 2 items, like the hydrogen beta filter, which if you want to see the Horsehead Nebula or the California Nebula, and then you put it away after spending $200 on a filter, and you never use it again. Camera holders are very popular nowadays, especially for your cell phones, and you simply put them around the eyepiece, and they align the camera lens with your eyepiece, so if you're looking, say, at part of the moon and you saw Tycho looking so fantastically bright and pretty, you can take your photo immediately through your Android or your iOS phone. A word of warning, do not buy a solar filter that screws into your eyepiece. Never, ever, because the light is concentrated by the mirror, comes up, comes into the eyepiece, shatters the filter, shatters the eyepiece. You can go blind, you can get glass in your eye. Never, ever do that. And I think that's about it. There's some websites, if anyone is interested in following them through. And that's the presentation.
Thank you very much. More about like things that a new person would maybe find helpful. Plus, I'm going to throw in a few little tricks that I've learned that maybe even some experienced people might find helpful. So they kind of fall in these categories. So planning the observing session, being comfortable while you're out there observing. In Ohio, dew is a big problem if you observe, especially if you observe all night. So how do you control your dew? Preserving your night vision. There's a lot of things that are helpful for that. Steadying the field of view. Having a nice rock steady mount, or even if you're looking at binoculars, you'll find having something to steady them will really improve your observing experience. How do you find things? So how do you navigate? And then I have a few miscellaneous things. So for planning the observing session, one thing you want to do is you want to make sure it's going to be clear. And the veteran astronomers in here know about the Clear Sky Clock. So this is a website that you can go to. It's clearskyclock.com. You use the planisphere, which you basically just you have one of these guys, and you rotate the date and the time to where you want it to be, and it'll show you what the sky looks like at that hour and day of the year. And finally, you can use planetarium software. One that I use a lot, which is good for telling you when satellites or the ISS, the International Space Station, will be overhead, also has a nice little planetarium software that's really easy to use. So here's the Clear Sky Clock for Perkins Observatory. So it looks pretty good. Lots of blue squares. There's a legend that explains what all of these are. But basically you want whole vertical row of blue means it's good to go out observing. And they have these clear sky clocks for a lot of our observing locations, like the John Glenn Astronomy Park. This is this is the planetarium software on Heavens Above. Again, you're just going to basically put in your date and your local time, and it's going to show you what the sky will look like and what planets there are. Yes, I'm sorry, yes, you have to put in your observing location. So creature comforts. One of the things that a lot of people underestimate is how warm you need to be. Because when you're out observing for a long time at night, it can get quite chilly. So even in the summertime, I will usually take a hat with me to keep the heat from coming, off my head. I'll always have a jacket with me, so that's important. It's important to stay hydrated, to have like cooler and snacks. I've got my camp chair here. It's good to just lean back, use it for your binoculars. Mosquito repellent, very important, especially when they're carrying, viruses and things. What I recommend is you use one with DEET, but not more than 25% DEET. If you use one that's more than 25% and you get some of that on your hands, and then you touch your plastics or rubber, it'll dissolve them. And lots of things on our telescope, have like plastic or rubber or cover our binoculars. So I would recommend not even taking anything with more than 25% DEET. And some hand towels to wipe the DEET off of your. Controlling dew. So normally when I go out, I come out outfitted with a battery and a dew controller. It has lots of little ports, and you have these dew strips that provide just a little bit of heat, and it keeps your lens just a little bit above the ambient temperature, and that's enough to keep the dew off of it. But of course, carrying a heavy battery and hooking all this stuff up takes time. So I found a nice little trick when I'm being lazy or just going out for an impromptu session. This is called a lens muff. Brad has decided, rather than paying the $25 that these things cost, a sock works really well too. These are designed to fit 3 of the chemical hand warmers that you would normally use, and you just put them in there in the sleeve, and then it's got Velcro on it, and so you just wrap it around your telescope or your camera lens, and it does a really good job of keeping the dew off. And it's a lot lighter weight than carrying the battery and all the accoutrements you need. And the towel. This is really good for protecting like your star charts and your books. So a towel is just essential astronomy gear.
Oh, yeah.
Preserving night vision, you probably already know about red lights. I like to have one that's dimmable because you want to use the least amount of red light that you need to read your star charts or to operate your equipment. Even red light can destroy night vision. They make special red film sheets for shielding things. One natural source of light pollution that Joanne mentioned is the moon. So a moon filter is a really good thing to preserve your night vision. Tail light repair tape can be found in your automotive section at Walmart. And this is like stuff, it's to repair broken taillights, but you can use it to create a little instant red light flashlight. These are great for outreach programs where most people won't have their own red light, but if they use their cell phone light, just put a little piece of this tape over it, they have an instant red light. It's also good for masking the lights inside your car. Glow-in-the-dark tape. This is really good for not bumping into things, so I get some glow-in-the-dark tape that you can also get at Walmart. and I put it on my chair and maybe my tripod legs. That way you won't bump into them in the dark. And finally, if you want to be the ultimate geek, astronomy geek, you get one of these. And this has got a red tint on, so you all look red right now. And but this is what you do when somebody is getting in their car and leaving your site, or there's a car coming in. You put on one of these, and it just protects your until they turn off their car headlights and stuff like that. So if you really want to look like an astro geek, that's steadying the view. I mentioned it's good to have some kind of tripod for your binoculars. I have a monopod, which is really portable, and it's got a trigger grip ball head, and I put my camera L adapter, my binocular L adapter, it's on top of here, and then you put your binoculars in here, and then you sit back in your chair and you just point it wherever you want, and it really, really helps give you a good, steady binocular view. Of course, having a good chair is also very helpful because it steadies you and you're very comfortable and can observe. So navigating the stars, I like to have a unit finder, like a red dot finder, as well as a magnifying finder. So here's your magnifying finder. Here's like an example of a red dot finder. Binoculars are good for sweeping in a lot of sky, finding things. Star charts, I have a few that I recommended. When you get old like I am, having your reading glasses and a magnifier. This is one I found at a pilot shop, and it's actually a magnifier and a red light in one. And so it's got a little red light on it, and this is great for reading your star charts. And then you can use less light and preserve your night vision. Jason gave me this idea. This is a music stand. I have a portable one that collapses, and you can keep all your star charts in it. Oops, I'm out of time. I went over. Okay, I think I'm almost done. So here's some examples of charts I recommend. The Pocket Sky Atlas is a great one. This is the beginner. The ultimate atlas. I finally found it. It's the Interstellarum Deep Sky Atlas. And I have it here with me if you want to see it after the talk. It's expensive, but it's the best atlas. It's the only one you'll ever need after that. Miscellaneous accessories that come in handy. I've got my sand-free mat that I take the J-gap with me, because that way if I drop an eyepiece, it might not shatter on the pavement. A step stool, so if you're vertically challenged like I am, now I wouldn't need it for this telescope, but if I want to go look at Brad's 18-inch Dobsonian, and maybe he forgot to bring his ladder, I just keep this one in my car, and I'm ready to go. And this one collapses down. White light flashlight is always good to have for emergencies. Lens cleaning supplies. I have a little bulb blower. I have a whole lens wipes. You never want to take your sleeve or anything in wet lens. I wear contacts, so I bring extras. And then Jim Schultz gave me this idea. If you have a voice recorder, you can actually record your observations. You can say, M51 looks really good tonight. I can see the trail of stars leading to NGC 5195. And then you can go home and record everything. And finally, of course, a green or blue laser. These are especially good for outreach. And they're super bright, and I'm sorry I blinded Isaac in an outreach program. You still can't see. But these will actually, lead all the way up. It appears to lead all the way up to the stars, so you can point things out to your friends. Or you can use your binoculars. You can find something in binoculars, and you can say, what's that up there? And then your friend with the telescope can point at what your laser is pointing at, and they'll say, oh, that's M51. So, all right, so that's all I have. But I have these things up here. You can come look at them afterwards. So, thank you.